Hello everyone, welcome to our algorithm YouTube channel. So today we are going to solve Leetcode daily challenge. The name of the problem is binary tree level order traversal. The problem statement is given the root of a binary tree, return the level order traversal of its nodes values, that is from left to right level by level. Okay. So we will discuss BFS approach first, then we will see DFS approach. So let's move to the BFS approach first. We are given a root, we are given a binary tree. Okay, so let's firstly draw the binary tree. A binary tree is a tree in which each node can have at most two children. Okay, so I'm drawing this the sample test case. Okay, so this is our tree. Now what should be the output if I do the level order traversal of this particular tree? Okay, so it should be a 2D vector, okay, in which each vector represents the corresponding level. Okay, so let's say this is my this is going to be my first level. Since the first level has only one node, so it should contain three. This is my second level and this is my third level. Okay, so the second level should have must have 9 and 20. Okay, and it is itself a vector, and the third level should contain 15 and 7. Okay, so this must be our desired output. Okay, so what we can do, we can use BFS approach here, breadth first search. So in order to use BFS, I can use Q. Q is a data structure that is based on first in first out FIFO. Okay, so but my approach is going to be, let me explain you. Firstly, we will use a queue. Let's say the name of the queue is queue. Okay, and what we will do, we will insert the root node first in this queue. Okay, let's say first the first value, root value is 3. Okay, so instead of storing values, I will store the address of that node. Okay, so it means that our queue will be of type tree node. And why I am doing so? Because uh, with the help of the node that is stored at the queue, okay, I want to get the left subtree as well as the right subtree. If I would have taken the integer value here instead of taking tree node pointer type, what would happen? I won't be able to get the address of that party. Suppose I am storing 3 first. Okay, so this is integer and I am storing it into queue. So this is my queue. So can I get 9, this left subtree from here, this one? No, I can't. Why? Because I am storing integer. Okay, that's why if if I would have stored the address of 3, then I can get the address of the left subtree and right subtree as like easily. Okay, so in the queue I am going to store, firstly I am going to store the root node, the address of the root node. Okay, so let's move to the approach. So let's start from a lever order function. Okay, so I am calling a helper function here. Let's move to the helper function. Initially I have declared an answer vector. It is a 2D vector of integer type, and as I told you, each vector in this 2D vectors represent the current level. Okay, initially if the root initially if the root node is null, initially if the root node is null, then I just had to return the answer vector. Okay, otherwise I will declare a queue. So as I told you, the queue has to be of tree node type, because from the current node we want to get the address of the left subtree as well as the right subtree. Okay, and since the very first node is a root node, so I am going to push it into the queue. Okay, now suppose I have stored all the nodes, all the address of all the nodes in the current level. Suppose like at the first level we have only 3. Suppose I have stored the address of 3, okay, in my queue. So in order to get the intuition that this level, the traversing of the current level has finished, I will insert null, okay, in the queue. This should be the address. That's why I'm writing it add address of 3, as well as I am pushing null, so that I get the idea that this the traversal of the current level has been finished. Okay, so I have pushed null value in the queue, and side by side I am also maintaining my label in the answer vector. Initially, since like root is not null, so our answer vector must contain at least one label. Okay, think about it. Answer vector must contain at least one label. Okay, that's why I am pushing a empty vector into the answer. Now let's traverse q till the size becomes greater than 1. Okay, now when the condition of q size become when the q becomes equal, at least obviously when we are at the bottommost level and we have traversed all the nodes in that particular level. Okay, so initially now let's move into the this while loop. I will get the front value that is stored at the queue into current node, and I will pop it out the like front value from the queue. And if the current value, if the current node is equal to null, what does it mean? It means that we have already processed the last level. Okay, we have reached the end of the level, we can say. So let me give you an example. Suppose initially this is my queue. Now I will go inside the while loop. Okay, and I will take this front value will be first node will be equal to, this is going to be my first node. Okay, uh, sorry, not first node, current node. Let's call it current here, current node. Okay, and here the current node is not equal to null, so it won't be go here. Now what would be my last position? Since I am going level by level, so I want to like the current last position represents the last level that is being traversed. So that thing I can easily get with the help of answer dot size minus 1, and at that particular level I will push back the value that is stored at the current node. Okay, and if the left value of the current, if the left subtree is not equal to left node is not equal to null, then I will push it into the queue, and same goes for the right node. If right node is not equal to null, I will push it into the queue. Okay, now I have got this 3. Currently it is not equal to null. This is my current node. Here it is not equal to null, right? The address of 3 is not equal to null, so it will go into the else part. Okay, what it would be the last position, because answer already contains an empty vector like this, so the size of answer is going to be 1. Okay, and sorry, and I am getting the last position as answer dot size minus 1. So answer dot size will give me 1, and minus 1, it would be equal to 0, right? and this would be my last position, 0. And at this last position, I have inserted the value stored at the current node. Okay. So now our vector will become like answer 3, and this value have been popped out from the has been popped out from the queue. Okay. Now I will this node, like current node, the left value is 9, so it will be pushed back pushed into the queue, as well as 20 is not equal to null, so it will also be pushed into the queue. Okay. Now our queue will become address of 9, address of 20. Okay. Now again I will go into the while loop. This time the current node is null. Okay, current node is null. So what will happen? Here the current node is null. So it means that we have already processed the last level. The last levels has been processed. Okay. So what should we do? We should insert an empty vector. Since we are going to add nodes at the new level. Okay. So here answer before that our answer was this one. So I am going to store an empty vector at the last. Okay. And we will keep doing this till the size of queue becomes 1. Okay. So at the end we will get all the nodes, and after this we will simply return answer. So this was all about our BFS approach. If I talk about the time complexity, since we are going to traverse all the nodes in the binary tree, so it is going to take big O of all the edges. Let's call all the edges. Let's denote all the edges by E. So it is going to take big O of E time. And if I talk about the space complexity, as you can see, at a time at like in my queue, we will have all the nodes at the specific level. Okay, so like either I will sometime I will like at first I will have 3 in the queue, then we will have 920 in the queue, then we will have 15 7 in the queue. Okay. So what I can say that if this is a full binary tree. Okay. So let's say the first level has one node, then we have 2 power 1 node. Okay. Then we have 2 power 2 node in the binary tree, like this one, full binary tree. And it let's call it 2 and n. Okay. N levels are there, and as you can see the maximum limit is just a second, maximum number of nodes can be equal to 2000, right? So it can be 2000. Okay. And this is nothing but a GP, geometric progression. I can simply found it with the help of formula a r ki power n minus 1 r minus 1, where r is the common ratio. Okay. This is going to be 2000. A is our first term, so it is 1 here. R is going to be common ratio, so common ratio is nothing but 2 divided by 1, which is nothing but 2, and 1. Okay. So 2000, 2 power 1, 2001. Okay. So let's take log both side, log of n. So it will be like n and log 2 2001. And it would be equal to around 15. Okay. So at most we are going to have 15 nodes. Okay, in the worst case. So it will take, if I say, like, if I summarize this, so it is like the space complex time complexity is going to be big of vertices. Okay, and the space complexity is going to be big of w, where w is the maximum width. Maximum width means here the maximum width is going to be this one. Okay, so big of w. Now let's quickly discuss about the DFS approach. uh, let's this draw the same example again. Now what I will do in the DFS approach, I will iterate from the root node, but I will also maintain a depth of a variable. Let's call it depth. Okay, so initially depth is initialized with 0 in the main function, and I will call it like depth, and let's call the current node. I'm calling it cur here. Okay, so I will call. Now once I when I will go in the left subtree in the DFS approach, I will call for the left node by like if I'm calling it for the left node, what I will do, I will pass the address of the left node, which is nothing but cur left, and since this is at the one depth below the current depth, I will pass it as depth plus 1. Okay, and same I will do for a right subtree, depth plus 1, right? And I will check whether this depth is equal to or greater than the size of the answer. I'm also maintaining our answer vector, answer 2D vector. Initially it is empty. Okay, and I will check whether at each recursive call, just after the recursion function is called, I will check whether the depth is going to be greater than or equal to the size of the answer vector. If it is so, then I will insert an empty vector into the answer vector. Okay, answer 2D vector, I will insert an empty vector, and at the like last position, last index at the end, I will store the node value as well. Okay, so here's my code. So let's move to the level order function. Here I have declared an answer vector. Answer is a 2D vector that stores all the nodes at the corresponding levels as a vector. I am calling helper function here. Let's move to the helper function. I am passing current root. Initially we will pass root. Okay, and 0 denotes the current depth. Initially the depth is going to be 0. I am also passing answer 2D vector as a reference. Okay, so if the current node is equal to 0, okay, so I will simply return. And if the current, this is my base case, okay, if the current level becomes equal to the size of the answer, which is our 2D vector, then what it means that we are exceeding the indices of the answer vector. So I will insert an empty vector to increase the size of the answer vector, and at the current level, like this is our depth. Okay, current level means our current level. I will insert this is nothing but depth. Okay, current level. So in the answer, at the current level, I will insert the node value, current node value. And if this is not the case, then simply I will, at the current level, I will insert the node value. And if the left node of like the left subtree, the first node in the left subtree of the current node is not null, then I will call helper function recursively for the left subtree, and same I will do for the right subtree. Okay, so as you can see, why I am writing this current node equal to null, because here I am checking before calling left subtree. I am checking now कि whether left current node left is null or not. Then I am calling for the left subtree, and same goes for the right subtree, right? So why I'm writing this? This is because the current node can be null as well. Okay, the root node, sorry, the root node can be, the very first node can be null as well. For this I am simply returning it. So initially, let's suppose root is null, so answer will be empty. Okay, and we are calling root 0 answer. Since we have found the root current node, which is our root node equal to null, so I will stop the recursion of current function. I will return it. I will stop the function from further execution, and I will simply return answer. Okay, so that's all about uh, today's Leetcode problem. So let's before ending this, let's discuss about the time and space complexity taken by DFS approach. As you can see, okay, we are going like if I talk about the time complexity, we are traversing all the nodes, right? Firstly we are traversing 3, then 9 will just a second. Firstly 3 will be traversed, then 9 will be traversed, then 20, 15, and then 7. Okay, so we are traversing all the nodes in the given binary tree. Okay, so time complexity is going to be nothing but big O of n, or let's say big O of v, big O of v, where v denotes the total number of vertices in the given binary tree. Okay, and what about the space complexity? Just give it a thought. Okay, so we are going at max, we are using the system's stack by what amount? At most we are going at the depth, right? At most, think about it. At most we are using the system's stack equal to the size, like we are consuming the height of the binary tree. So it is going to be nothing but big O of h, where h is the height of the maximum height of the given binary tree. Okay, so that's all about today's Leetcode daily challenge. Thank you very much. If you have any doubt, you can comment down your query.